Okay, we'll go ahead and we'll get started. So we're officially starting on Galois theory. And somehow there's a lot to say, and even to write down like the main theorem takes a whole page. So I put it in the handout. So if you haven't already looked at it, you should pull up the handout for this week. For weeks 11 and 12. And actually, so the handout for this week is not just the handout for this week, it's the handout for the next 2 weeks. And we'll be doing Galois theory, so starting with the basic statements today and building up through some applications through next week. But there's just one homework assignment on the material. It's not due until the 13th of April. So you have 2 weeks for this assignment. It's probably a little bit longer than the assignments have been, but hopefully not twice as long. I don't really know. Maybe the level of difficulty of the exercises is slightly higher, at least some of them, than it's been. But then there have been some hard exercises before, so maybe it's not any higher. But there are 7 exercises, and then you still only have to turn in 1 problem. But there are 3 problems to choose from, and they're all really interesting problems. So I think like this assignment, so maybe more than past assignments, I would recommend, even if you only have time to do 1 of the problems to turn in, like do take a look at all of the problems. And even if you don't work them out fully, like think about all the problems. So like one of the problems is about symmetric functions, which is sort of a fundamental result. We'll mention something that uses this result later, although it will just be a side note. So that's for problem 1. Problem 2 is like one of the classical applications of Galois theory, sort of understanding so depending on how you phrase it, it's not really an application of Galois theory, but you can think of it in a nice way as an application of Galois theory, and so that's how it's written here. And so for which n is the regular n-gon constructible using a straight edge and compass? So this is sort of one of these classical problems that Galois theory can be used to solve in maybe a surprising way. And then there's also a part of the proof I've sort of left as an exercise. So the proof, and there's a key lemma that you use when you sort of prove the fundamental theorem of Galois theory. Like basically all of the work is actually in this key lemma. And a lot of the key lemma itself is not that complicated, but the key lemma sort of has the proof is a couple paragraphs long, but like if you write it out in a couple of paragraphs, like you sort of miss seeing that it's connected to like some bigger ideas. So here the proof of that lemma is sort of written out with some bigger ideas. So anyway, all of these problems are interesting, and I recommend at least looking at all of them, even though you still only have to turn in 1. And again, not till April 13th, so you have some time. Okay, so that's what I wanted to say about the handout. And then, so yeah, at the start of the handout, the basic definitions in order to state the fundamental theorem of Galois theory are given, and then the fundamental theorem is stated. The statement I wrote down, I think, is probably pretty close to what's in Dummen and Foote. Maybe I left out one thing. Maybe didn't use, it's not maybe not written exactly the same, but same idea. And then it sort of just explains sort of some of the main corollaries, and like just so you have them all in one compact place for working on the homework. And I still recommend reading in Dummen and Foote. I think the reading for the next 2 weeks is like basically all of chapter 14 if you'd like, but some other statements you'll actually need on the homework, I think, are essentially contained in what's written at the top of the handout. Okay, so good. That's what I wanted to say about the handout. And so today I'm just going to talk about Galois extensions and the fundamental theorem. We won't prove it, but we'll talk about the statement a little bit, and we'll sort of discuss some related ideas. Okay, so and somehow, and what is Galois theory about? And it connects two somewhat disjoint ideas. So it connects the study of roots of polynomials to field automorphisms. And essentially, it just organizes it organizes in a nice way some things we've already been seeing happening in field theory. So let me recall one fact that we already talked about. So if L over K is a field extension, and F of X is in K of X, so F is a polynomial of coefficients in K, then the Galois group, then automorphisms of L over K act on the roots of F. So, and the roots of F inside of L. So just sigma of alpha is also a root. So when I mean on L over K, this means field automorphisms of L that are the identity on the K. So not only do they send K to itself, but so they act as the identity map on K. Okay, wait, so these field and an automorphism in particular acts on the whole set, and a field automorphism is in particular a set automorphism. And well, and it can preserve some subsets. And so, and what this is saying is, and roots of polynomials are subsets that are preserved by this action. Okay. So this is the start of the connection. And the reason is just if, so let me recall the reason. If some a(n) alpha to the n is equal to 0, then sigma, the sum of a(n) alpha to the n is equal to 0. These a(n) are in k. Then since it's a field in automorphism, this is the sum of sigma a(n) sigma alpha to the n, sigma of 0. Sigma 0 is 0. This is sum of a(n) sigma of alpha to the n. So the point is, since you preserve these coefficients, since 0 is 0. So that's the starting point. But on the other hand, so let me bootstrap off of that a little bit. So observation, well, if L is equal to K alpha 1 through alpha n, say L is generated by these elements. Well, let me take, and then any element in aught of L over K is determined by what it does. So it's determined by sigma alpha 1, sigma alpha n. So if you know what it does to each of these things that generates the field, then you know what it does to the whole field. So this is essentially a thought experiment to confirm this is true. but sort of grammatically it sounds true at least, and so you can check from the actual definition that this is true. So it's determined by this, and sort of each. So if I denote by m alpha I the sort of minimal polynomial of, so if the alpha I are algebraic, and I denote by m alpha I the minimal polynomial of alpha I over k, well, then sort of sigma alpha I sort of has to be contained in sort of the roots of m alpha I and L. So somehow, the number of, like how big the automorphism group can be is controlled by, so how big the automorphism group can be is controlled by the roots of these polynomials. So in particular, like just as an example, like this implies that ought L over K is finite. If, in fact, this is an if and only if, let me just say it. If L over K is finite. Okay, so, and in fact, you can do a little bit better. So we sort of a link between these, turns out there's a link between these two fineness. So let me say the following, well, really just a lemma. Oh, sorry, I guess in case it wasn't clear where this sort of L degree of L over K being finite was coming in. Remember, we proved the degree of L over K is finite if and only if L is finitely generated and algebraic. So that means sort of exactly you're of the form K alpha 1 through alpha n for some algebraic things. Okay, so lemma, if L over K is the splitting field of a polynomial f, then how do I want to say this? Then here, I'll try to do it this way, but I might screw up. So first, let me say this is less than equal to the degree of extension. And it's equal. Yeah, I'll say, okay, good. So I'll say it this way. Equal to it. So with equality, if and only if f is separable. So to say it this way, let me do an irreducible polynomial. So you could say, otherwise. I mean, so let me say the idea. Okay, so I have, yeah, so this is what I'm saying is sort of not an optimal statement, but that's fine because we're not, this is just an And it's an example lemma. It's not a lemma that we're actually going to need. So somehow be okay. So what is the idea? Well, okay, so I have let me just number the roots. So okay, and so each of these, like, I know sort of L is equal to K alpha 1 through alpha n. And I know, so I know it's equal, yeah. Okay, so I'm in sort of the step from before. And suppose, I mean, sigma contained ought L over K is sort of determined by where it sends these roots. But it really sort of has to permute these roots. Okay. I mean, so somehow it has to send these roots to, like, what, and these are all the roots of f. F is the minimal polynomial of any of these alpha I, so sort of sigma of alpha 1 has to be sort of some other alpha I. So and it permutes these roots. And so, and another way to say this, by the way, is that, like, once you've numbered the roots, you get an injection to the symmetric group. So really, I mean, so you get a map from sort of automorphisms of L over K to automorphisms of the roots of F in L. So that means just the set. So this is sort of just permutations of the set. And then if you number the roots, this is the symmetric group. Okay, so that's sort of another way. Saying that this map is an injection is another way of saying that an automorphism is determined by how it permutes these roots. Okay, and then so and if you want to sort of see there's some relation between the size of the automorphism group and the degree, well, what you could do is you can just build up, and you can build up an automorphism one element at a time. Just like you can sort of build up this field by sort of adding sort of one thing at a time. So like we start, and we want to build, sort of to build sigma. Well, first we should say, what does it do? To alpha 1. Okay, so, well, let's try. And so we can just look at K alpha 1, which is sort of inside of L. And sort of sigma. We want to see where an automorphism can send this root. Well, in particular, like, let's just like forget about giving an automorphism of all of L at the start. Like, let's just see what that automorphism can do just on this subfield. So like, what are the maps from this to L? What are the possible maps? That sort of fix K. Well, I can send, and this is just isomorphic to Kx mod f of x. And so because of that, I mean, I can send x to any root. So that means, I mean, sort of I can send alpha 1 to any root I want. So because in this smallest field, the field generated by alpha 1 is sort of just abstractly kx mod f of x. And so to give a map from this to L is just to give a root of f of x. That means I can send alpha 1 to anywhere, to any alpha I. So I can send, so I get, so I'll call it sigma 1 from k of alpha 1 to L, such that sigma 1 alpha 1 is equal to I. So for any I can get this. Okay. Well, now now I'm just going to repeat. Now you sort of just repeat. So sigma 2 is going to be from k alpha 1, alpha 2, which is k sort of alpha 1 add alpha 2 to L. And so I have to say, where can I send alpha 2? Okay. Well, I mean, so I know sort of, and so this, and I'm sort of extending sigma 1. And this is sort of a little bit of a tricky part. So I'm no longer saying that this should be sort of the identity map on k alpha 1. I'm saying that sort of I have this automorphism, like this, I have this map from k alpha 1 to L. The sense of that is not sort of the identity map necessarily. It's sort of it's only the identity map if 1 is equal to I. And so I want to extend this automorphism I already have by sort of sending alpha 2 somewhere. Okay, but so I mean, let me write M. Okay, so this is gonna be a little bit funny, but M alpha 2. This is the minimal polynomial of alpha 2 over k alpha 1. So, and then, sorry. And so then k alpha 1, alpha 2, which is isomorphic to k alpha 1 brackets x mod. Let me just call this M, because otherwise it's going to get too much notation. Mod M of x. And so then that means I can send x to any root of so the following point of sigma M of x. So here this means apply sort of sigma to the coefficients, sort of sigma 1. Which is the minimal polynomial of yes, so this is sort of contained in all of x. Okay. somehow, yeah, so the point is, okay, so again, there are going to be a degree of M choices for this. So I don't know how, yeah, I don't think I set this up in like a great way to explain this, but this polynomial sigma 1 of M, like it's going to, just like M, like this M of X, yeah, so let me say it this way. No, sorry, an M of X divides F of X, this polynomial we started with, right? Because alpha 2 is a root of, like alpha 2 is a root of F, because all these alpha i's are roots of F. I mean, M is just a proper divisor because we know F is no longer irreducible. Like, so, it's okay, but because it's over K of alpha 1. So that means sigma of M, so sigma 1 of M of X, so also divides F of X. Well, sorry, divides sigma 1 of F of X, which is equal to F of X. So I just sort of apply that, like, just apply the automorphism to all of the coefficients. But I mean, because F has coefficients in K, it's preserved by sigma 1. Sorry, not apply that. And sigma 1 is not an automorphism, it's a map, sorry, from K alpha 1 to L, but and it sends K, like it's the identity on K. So I can think of K as being a subfield of abilities, and it's the identity on K. So that means it sort of sends F of X to F of X still. So that means this sigma 1 M of X is a sort of divides F of X. So that means all of its roots, like all of the roots, are in L because L is a splitting field for F. So it has in F. So our roots are in L. So L is a splitting field of F. Okay, so I have degree of M choices. So okay, so I sort of picking any of them, sort of, and then these are just sort of other. I mean, this degree M choices, like they're just other roots of F. So there's other these alpha i's. So I get sort of sigma 2 extending sigma 1. And where in M was equal to K alpha 2, so K alpha 1 is the degree of this extension. So the point is, the number of options I have for extending sort of, okay, so let me go back. I mean, first we built this sigma 1. And we know, like, sort of the degree of K alpha 1 over K was sort of the degree of F. And we also knew we had sort of the degree of F choices for sigma 1. So we could send alpha 1 to any of these other roots. So okay, so here I'm really doing the separable case. Otherwise, we'd have fewer than the degree of F cases. But in the separable, then these really all distinct. So we have exactly sort of degree of F choices. So sort of the number of automorphisms, like the number of options we have for building our automorphism are the same as sort of the degree we're going up. And then we repeat. And sort of the number of choices we have for sort of extending our automorphism to a new one is the same as the degree of M, which is the degree of this extension. So, and then you just repeat. I mean, now you have to extend to sigma 3. So that's sort of a map from K alpha 1, K join alpha 1, alpha 2, and alpha 3 to L. But you just do the same argument. You see like the number of choices you have for extending sort of the automorphism you built up to that point is equal to the degree of the extension. And so you keep on repeating, and then, well, the number of choices multiplies, and the degree multiplies in the tower. So you sort of deduce that the size of ought L over K is equal to the degree of the extension, if separable, if F is separable. And less than equal to otherwise. And really less than otherwise. And the point is, if F is not separable, then already in the very first choice you make, you have fewer options. Because in this very first choice, like for sigma 1, you had fewer than, like you'll only get roots of F, and there are fewer roots of F than the degree of F. So you already sort of have fewer. Okay, so that's the idea. And this is somehow and this is a way to see that sort of there's a notion, like there's this link between separability and the number of automorphisms. Sort of fundamental to Galois theory. Okay, so let me sort of make some actual statement of Galois theory, or at least, and again, you should probably just look at what's written in this handout, but let me state a definition sort of at the start. So definition theorem. L over K finite is Galois if any of the following hold. So any of the following equivalent conditions. Okay, so one is that you have this just identity of sides to automorphism groups. Okay, then the two is the only things fixed by the automorphisms L over K are K itself. So, and this is like you have to stare at this. If you like the first time you see this, you have to sort of stare at this for a second to understand why this like is not a tautology. But so let me I guess define this thing. So when I write sort of some set to some group that acts on that set, that means the fixed points for that action. So this just means L in L such that sigma of L is equal to L for all sigma in L over K. So this means all of the elements of L that are fixed by every automorphism in this group. Okay, so and by definition of L over K, these are all of the automorphisms that fix K. So definitely sort of K is contained in here by definition, but there's no reason there can't be more than K in there. I mean, a priori, like, so just for example, and we've seen this already. If you look at like FP, T to the 1 over P over FP of T, I mean, the only automorphisms, yeah, so this one, there are other examples, but this is sort of, the only automorphisms that send T, an automorphism is determined by where it sends T to the 1 over P, but there's only one root of, like there's only one P root of T. So it has to send it there. And so there's sort of only a trivial automorphism of this. So like ought of FP, the automorphism of FP T to the 1 over P that fix FPT just equal 1. So then in particular, like the fixed field for this group of automorphisms is the full extension. So that's an example of how this breaks. I think this was a homework problem. So I think this is a homework problem for the homework assignment, etc. So there's a freebie. That's why that extension is not Galois. So this why it's sort of non-trivial condition. I mean, this was sort of a fancy example. I mean, a less fancy example would be, so if you take a generic polynomial and you adjoin a root, it turns out that field's not going to have any automorphisms. I mean, somehow the typical field you get by adding a single root doesn't have any other roots contained in it. And so, but somehow, and this is an example that's a splitting field that satisfies this. And you can get many other examples that don't satisfy this just by not taking a splitting field. So taking an extension that's not a splitting field. Excuse me. Okay, the next condition is L over K is separable and normal. So what that means is if you take an element of L, then it has a separable minimal polynomial. Well, let me say it together though, because this normal means something too. So separable means sort of every element has a separable minimal polynomial. Normal means if sort of any irreducible polynomial that has one root in that field has all of the roots in that field. So together, that means that sort of if for any element in L, any root of its minimal polynomial, like for any element in L, its minimal polynomial has sort of that, like its degree worth of distinct roots in L. So it's separable, so it has degree distinct roots in the splitting field, and so it's normal, so sort of all those roots are sort of in L. So that's what that means. And yeah. Probably other people prefer to write those separately, but then somehow I like to see it at the same time. And another way you say this written commonly is the normal part. Another way you'll see that written is like if an irreducible polynomial over K has a root in L, then it splits into linear factors over L. So that's another way to say normal, what normal means. Okay, and the last condition is L over K is a splitting field. Of a separable polynomial. Okay. So, I mean, these conditions all look pretty different. And I mean, the fact that they're equivalent is sort of very powerful. Okay, so a remark about sort of how you see this. So some remarks about how you see this. Again, so you can, and if you want to see a full proof, you can sort of look in Dumb & Fuller or any other textbook. But let me just sort of outline the idea. I mean, 4 implies 1 and 2. We basically just did. And you can go back to that thing we just did, and then, well, I mean, I did it with an irreducible separable polynomial, but you could just take a product of irreducible separable polynomials and sort of do the same thing, and then that's sort of a separable polynomial. So if you take a product of distinct ones, you can do the same thing. You sort of just build the automorphisms up one step at a time, and like, well, then we got this equality from doing that. And then also, like, if you like think about sort of the choices you're making while you're doing that, you'll see like the only way you can get, I mean, somehow you'll see, yeah, I guess, I don't know if you can get too easily out of it or not, actually. So let me just say, for applies one, we basically just did. I mean, probably it's not completely clear from what we did, though, that K is the fixed field of the automorphisms in that case, without doing something at least a little bit more. But okay, at least getting, and there are sort of quick ways to get to now in that setting, I think. To get sort of 4 also implies 2, I mean. And then 2, actually sort of like 2 implies 3 is easy. So the point is, let me sort of do a proof. If alpha is contained in L, then, right, sort of f of x so you can just look at the orbit of alpha under the automorphism group. So the automorphism groups acts. So you just look at the orbit under the automorphism group. And you can check this is the minimal polynomial. And the point is, like if I sort of apply sigma to all the, so if I take, and the point is to see that this has rational coefficients. So like I know, so it has coefficients in K. You know that's whatever the minimal polynomial of alpha is, like if I take some element in L over K and I hit it alpha with it, like I'm going to get a different root of that minimal polynomial. So this is sort of something we've already used lots. So like, like all of these elements are roots of the minimal polynomial. So the point is to see that just literally those are the only roots and they all appear with multiplicity 1. And so to see that, like that means you sort of write down this polynomial and you have to show that has coefficients in K. Okay, and this is exactly what, I mean, this gives you a way to check that something has, like that something's in K. So something in L is in K if and only if it's fixed by all these automorphisms. And so if I can just apply sigma to all the coefficients. So when I write sigma of a polynomial again, that means sort of apply sigma to all the coefficients. So that's going to be the product over all of these beta again of, well, x minus sigma of beta. But that's an any like an orbit, like any element of the group just acts by an automorphism of the orbit. So it just sort of permutes the orbit. So this is still the same polynomial. And like this is the same polynomial, just sort of with the roots reordered. So that means all the coefficients So this is for sigma in auth L over K. So all the coefficients are preserved by aught L over K, implies they're in K. So this part 2 gave you that they're in K. Okay, and then once you have 3, and 3 implies 4 is easily. Yeah, okay, good. So 3 and just takes elements to generate L over K and take the product of their minimal polynomials. And sort of, if you got the same minimal polynomial twice, just sort of get rid of it. Okay. So, the thing that is less sorry, the thing you need to be a little bit clever to see here, and the most powerful part of the statement then is actually that this sort of numeric equality implies this sort of somewhat stronger group theoretic equality. And so so let me check. So I always get this backwards. So you actually just need to know the following. Yeah, good. So if I know well, okay. I think you can get away with less of this, but let me just state sort of the key lemma, because this is say a stronger lemma. Maybe you need all of this. I can't remember now. Yeah. So the lemma is the degree. So if G, okay, so let's say this way: if L is a field and G is a subgroup of L, then the degree of L over the fixed field for G, the size of G. Let me say a finite subgroup. So and this is true for infinite subgroups as well. If you so this is true for if you interpret all infinities as being the same. If you don't interpret all infinities as being the same, then it's sort of not true for infinite subgroups. But anyway, we will just need it for finite subgroups. Okay, so this is sort of what's listed. I think it's called lemma 1 on the handout, and the proof uses independence of characters plus a version of something called descent. That's explained in the problem. If you look in the proof in Dominant Foot, it doesn't really, and it's just some linear. It's a linear algebra. The argument you make is sort of a linear algebra argument. that looks a lot like that. It looks pretty similar to the linear algebra argument you use to prove independence of characters. So you don't sort of have to say anything fancy. But on the other hand, like, yeah, so this is what I was saying at the start of class, like the idea that goes into this proof is sort of a simple example of like a very powerful idea in sort of algebra and algebraic geometry in general, which is sort of, you can always, like, you can often replace like, and so in this setup, it's sort of the idea that you can replace working with a vector space sort of over LG that's with working over with a vector space over L that sort of has some action of the Galois of this group G on it. But let me, yeah. You can sort of see more about this problem. And this comes up a lot in algebraic geometry, though, for example. So just to sort of say a few words that might be nonsense, but depending on your background, but that's okay. I mean, somehow there's some real difficulties to doing algebraic geometry and related things over fields like the rational numbers instead of over the complex numbers. Like you probably already saw this last semester. I mean, like somehow the statement of the Null-Stellensatz is sort of much simpler if you use the complex numbers than the rational numbers. Because sort of you can think of sort of all of your points as being complex valued points instead of all of like your points are being valued in like different extensions of Q. And so anyway, then somehow like algebraic geometry over a field that's sort of not algebraically closed there's just sort of an added layer of complexity from this non-algebraically closedness that sort of contributes to everything. It turns out, like sort of in a sort of way that can be made precise, like doing algebraic geometry over over the rational numbers is the same as doing algebraic geometry over like an algebraic closure of the rational numbers, if everywhere you sort of keep track of like an action of the Galois group, of sort of a big Galois group. This idea is called descent. And so that it lets you sort of replace working with a situation that's sort of maybe difficult for some reason with working in a situation where things are simpler, and then you just have to sort of keep track of sort of a group that's acting on everything. That's a sort of a nice reduction to be able to make. Okay, so let me not say any more about that, but once you have this, and you use K is contained in aught L over K. So, or sorry, in L over K. So the degree L of K is equal to the degree from L to so if okay, so I probably didn't even need this. So if this is equal to so what I'm trying to prove. Oh yeah, okay, good. So by the lemma, this is equal to the automorphisms, the size of this automorphism group times okay. But that means if the degree of L over K and the size of this automorphism group are the same, so if these are equal, then this other index has to be 1. So, and that was what we sort of had left to prove. We had left to prove that sort of this first condition in the definition implied the second condition. Okay. So right. So let me note the following, sort of. And it's about, yeah, and so this lemma, you use it in proving, well, we just used it. You also use it in proving like the other aspects of the fundamental theorem of Galois theory. Let me just make a sort of further remark about it. And you can make a similar argument. So a similar argument shows always that the number of automorphisms is less than or equal to L. Okay. So the number of automorphisms, in fact, is a divisor of the degree by this equation. So not really a similar argument, really the same argument. This is always. Okay, and so then okay, good. So I just wanted to point that out, and this is useful to have in mind. And then also I want to point out sort of that the lemma shows that L over LG is Galois with group G. So I ought, in saying, when I say it's Galois group G, that just means the automorphism group of L fixing LG is equal to G. So certainly G is contained in there. On the other hand, G is contained in there. On the other hand, we know the size of the group is the size of G, sort of by this by the lemma. Sorry. We know G is contained in here. Then we know the size of the group is less than or equal to the degree. But we know the degree is equal to the size of G, so that means sort of G is the whole thing. So you combine these two things, you get sort of this statement. So and this is useful in thinking about this first characterization of a Galois group. And it's not that like, the issue is not that there could be too many automorphisms. Like the issue is always that there could be too few automorphisms. And so this equality is saying sort of there's this equality is saying there's as many automorphisms as possible. And like we already saw this sort of, so this inequality is based on this lemma. We already saw this same inequality sort of more explicitly, at least in like one example when you sort of had a splitting field. When we did this other lemma, we already got this inequality sort of for the splitting field, and sort of, you can sort of also like make a similar argument to show it in general. So okay, good. Yeah, okay, so that's sort of organizing some relations between Galois groups and sort of the properties of roots of polynomials, or sorry, between Galois extensions or properties of roots of polynomials. The other thing I really wanted to highlight that we did is this equation. And this is really nice to have a formula for the minimal polynomial in terms of sort of the automorphisms. So, and this equation is sort of true in any Galois extension. So we use it in the proof, but I also make this note. If L over K is Galois, then the roots of the minimal polynomial of alpha in L are just the Galois orbit. So anything you can hit by an automorphism. So again, so the easy part was that anything you hit with an automorphism was still a root of the minimal polynomial. Like the thing that sort of Galois theory tells you is that's really giving you all, like the thing that sort of this tells you is that's really giving you all of them. So in particular, so if in particular, if f is a separable polynomial, not necessarily irreducible, and L is a splitting field, then, well, it's just a little bit of work to go from what I just said. So the theorem told us, that in this case, L is Galois. So we know that L is Galois. So we know this is a Galois extension. So we know sort of this note we applied. This note applies. So this means if you take a splitting field and you take of a separable polynomial, then the irreducible factors of f so in Kx are in bijection with the orbits of the Galois group of L over K. So sometimes to emphasize that extension is Galois, instead of writing odd of L over K, you write Gal of L over K. You say Galois group. So the orbits of the Galois group acting on the roots of F. And this is sort of a powerful idea. This sort of translates like this arithmetic problem of factoring a polynomial into sort of a group theoretic sort of problem of just computing the orbits of some group action. This is sort of a useful perspective. Okay, so I think again, I've talked for a long time and forgotten to give you a break. Sorry, I feel like we're just sort of at that kind of point in the material where obviously if I worked harder, I would have thought and put sort of natural pauses in. So I'm sorry I didn't do that. But sort of we're at the point of the material where like it's easy to accidentally not do that. So I haven't. But so okay, so we'll end class early. So we'll end class in 5 minutes because you didn't get a break. And let me just say the fundamental theorem. Oh, so let me give you one. Sorry, this lemma we used. So I meant to give you a hint about something. If you are still struggling on exercise 4, part 3 on the homework that's due this evening, then there is a easy way to do it using this lemma. And since we've now learned this lemma, you are now permitted to do that. It can be done, and like there's a nice way to do it without using this lemma, but like using this lemma gives you a very short, can give you a very short proof of this number 4 exercise 4 part 3. So that this part where you're sort of computing what the fixed field is of sort of t goes to t plus 1. On the So okay, so I want to point that out. Good. Right, and then so what's the fundamental theorem of Galois theory say? And sort of, and it builds on this connection. And it says sort of the fundamental theorem says sort of intermediary fields, so if L over K is Galois, and intermediary fields where I'm bijection with subgroups of the automorphism group. And so you send M to sort of fix of M. So that's just all of the automorphisms that act by the identity on M. It's written on the handout, so I won't write it here. And a subgroup just goes to sort of the fixed field. Okay, and so this is, this is a bijection, and sort of it reverses inclusion, satisfies some other nice properties. You can sort of identify which sub-extensions are Galois. There's some nice interaction with compositums and intersections of subgroups and so on. So there's various nice properties of this besides just being a bijection. And like improving this now is no harder than anything. So we just justified when we were proving these definitions of Galois. I mean, proving this is sort of essentially just repeated use of this lemma. So of this lemma. It's a good exercise to go through and sort of try and prove some of these on your own, like some of the statements, but it's a little bit repetitive. Somehow you'll see very quickly why this lemma is so important, and like that's the main point. Like this lemma controls everything. Okay, so I just want to like this is an amazing theorem. Like, this sentence. Just for example, like, it's not even like without this, like, it's not even clear that like if I sort of take a field and I adjoin like if I take sort of a field that's generated by like 5 elements, like K, like 5 algebraic elements, like K alpha 1, alpha 2, alpha M. I look at that sort of extension of K. That only has finitely many sub-extensions. So here, and like one corollary of this is that any separable extension has sort of finitely many sub-extensions. So you can sort of just put it in a splitting field, and then sort of that will only have finitely many sub-extensions because they correspond to subgroups. And this is like really amazing. This says, somehow this says, I don't know, like there are so many different ways you could and just like if you look at like K alpha 1, alpha 2, like there are so many ways I can combine alpha 1 and alpha 2. I can look at like alpha 1 squared plus 7 alpha 2 plus 3 times alpha 1 alpha 2 and so on. And then like I could look at the subfield this generates. And like there's sort of infinitely many cool ways I could combine these things, and somehow I'm only getting finitely many subfields generated by them. So lots of different choices of these sort of crazy things like generate the same subfield for some reason. And like what this sort of tells you is like a lot of like apparent complexity in the roots of polynomials and the way like arithmetic interacts with taking roots of polynomials. While it's still like arithmetically complex, there is some governing structure that eliminates that complexity. Like there's sort of unexpectedly many ways, like unexpectedly sort of simple relations between these things. Okay, so and like another corollary is sort of any extension that's generated by finitely many separable algebraic elements is in fact generated by a single element. So this is the primitive element theorem, probably in a way you're more used to. So again, on the last homework, or the homework that's due tonight, you prove that the primitive element theorem is equivalent to having only finitely many sub-extensions. So having a primitive element is equivalent to that, and so. But this is, like everything about this statement is like the statement of the fundamental theorem is amazing. Like even down to just like the strong finiteness imposes. Anyway, it's an incredible theorem. and it's incredibly useful. And like, it lets you sort of boil down sort of questions about roots of polynomial that are sort of, I mean, somehow when you talk about them as being a question about roots of polynomials, are like really embroiled in like this extra arithmetic complexity. And lets you sort of take those problems and turn them into problems about finite groups, where there's sort of, and somehow what you do is like, in field theory and then Galois theory sort of like exactly like field theory sort of somehow like shows you the thing that is sort of atomic. Like the thing that's atomic is sort of not the roots of the polynomials themselves. Like it's sort of the extension those roots generate. And then like that's sort of the thing that's atomic to sort of many interesting problems. And then Galois theory sort of tells you sort of those sort of subfields sort of can be understood in terms of group theory. Like combining these two ideas is extremely powerful and led to the resolution of lots of like classically difficult problems about roots of polynomials by sort of recasting them as just simple problems in group theory. And that's what we'll talk more about the rest of it. But sorry, let's stop there, and I'll stick around if anyone has any questions.